Okay, think about something like throwing a ball straight up. You put effort in, right? There's force. The ball moves against gravity. It slows, stops, then falls back.
Hmm.
It feels like a whole bunch of physics ideas all tangled together: force, motion, energy changing.
Exactly. And what's great about the sources we've got for this deep dive is how they show these aren't really separate things. They fit together into a really consistent picture.
So, what have we got lined up?
Well, we've got some really solid material. We're going to dig into work, energy, and power.
Hmm.
We've got detailed stuff from Sci physics resources, which are great.
Okay.
Plus a YouTube transcript that actually shows the work-energy theorem visually, which is helpful.
Oh, nice.
And some interesting points from the University of Johannesburg about how students sometimes, grapple with these ideas, common sticking points.
Good stuff. So, the mission today.
Basically, let's pull out the key ideas. What is work? How does it connect to energy? What about power? And we want to make it clear, without getting bogged down in too much jargon.
All right, let's jump in. The big one first: work. Now, we all say work all the time. That was hard work. I've got work to do. But physics has its own very precise take on it.
It really does,
Yeah.
as the Sci stuff points out. In physics, work is done only when a force makes an object move.
Yeah.
And critically, it has to move some distance in the direction of that force.
Right. So you need both force and movement, and they have to be like aligned somehow.
Exactly. There needs to be at least some component of the movement along the same line as the force is acting.
Okay, here's where my brain starts to ache a bit. Think about like a strong man carrying a massive weight across a stage. Huge effort.
Oh, definitely. Looks like immense work. His muscles are straining, holding that weight up against gravity.
So he is doing work.
Well, yes and no. It feels
Okay.
like work, and his body is certainly working hard. But if we're strictly talking about the physics definition of work done on the weight, it's actually zero.
Zero. How?
Because the force he's applying on the weight is mostly upwards, fighting gravity. But the movement, the displacement, is horizontal across the stage.
Ah, I see. The force is up, the movement is sideways, they're perpendicular.
Precisely. And because the upward force isn't causing displacement in that upward direction, it's just stopping it from falling. No work is done by that specific force on the weight in moving it horizontally.
Okay, that's weirdly specific. So all that effort, the sweating, the straining, where's that energy going?
His body is definitely burning energy. His muscles are contracting and relaxing using chemical energy. But that energy isn't being transferred to the weight as physics-defined work. It's internal work within his muscles.
Okay.
Sciavula has that other example, right? Max pushing a wall. He gets tired, uses energy.
But the wall doesn't move.
Exactly. No displacement of the wall, so no work done on the wall, even though Max feels exhausted.
Got it. Force needs to cause displacement in its direction. Okay. So what about directions? You mentioned positive and negative work in the sources.
Right. This comes down to the angle between the force and the direction of movement. Positive work happens when the force, or at least a part of it, points in the same direction as the displacement.
Like pushing a car to get it moving faster.
Exactly. Sciavula uses that example. The engine
Sure.
pushes forward, the car moves forward. The angle's 0 degrees. Cosine of 0 is 1. It's positive work.
And they gave numbers, didn't they?
Yeah, 500 newtons over 20 meters gives 10,000 joules of positive work.
Yeah.
And what happens? The car speeds up. It gains kinetic energy.
Makes sense. You push it the way it's going, you add energy of motion. So negative work must be the opposite, pushing against the motion.
Precisely. Negative work is when the force, or a component of it, acts opposite to the direction of displacement. The angle is 180 degrees, cosine is -1.
Like hitting the brakes.
Perfect example, also from Sciavula. The braking force acts backward, but the car is still moving forward as it slows down. The work done by the brakes is negative.
And the calculation there.
They had 300 newtons over 25 meters, giving -7,500 joules, negative work.
And the source mentioned the car loses energy here, often as heat in the brakes. But importantly, it said the energy isn't lost overall.
Crucial point. That connects directly to energy conservation. The car's kinetic energy goes down, yes, but that energy is transformed mostly into heat due to friction in the brakes. It doesn't just disappear.
Okay, so energy is conserved, just changed form. That seems really fundamental.
Absolutely fundamental. It underpins everything we're talking about.
So work can be positive, adding kinetic energy, negative, removing kinetic energy, or zero, like the strongman example. But usually there's more than one force acting, right? Like friction is almost always there.
Good point. Real-world scenarios usually involve multiple forces. And that's where we need the idea of network.
Network. So the total work.
Essentially, yes.
Yeah.
It's the sum of the work done by all the individual forces acting on the object. Siavula's car example comes up again.
Okay.
Imagine the engine pushes forward, doing positive work, maybe, say, 6,000 joules. But friction pushes backward over the same distance, doing negative work, maybe minus 2,000 joules.
So you just add them up. 6,000 plus negative 2,000.
Exactly. The network would be 4,000 joules in that case.
Mm-hmm.
You just sum them algebraically, taking the signs into account.
And that network, the
Yeah.
total, is what really matters for how the car's motion changes.
Precisely. Which leads us straight into the work energy theorem. It's a really powerful idea connecting work and energy change.
Okay, the work energy theorem, what does it state?
It states that the net work done on an object is equal to the change in its kinetic energy.
So one net equals delta KE.
Exactly, delta KE, or sexy final K initial. The YouTube transcript we look at actually uses this formula explicitly.
So it connects the total work directly to how much the object speeds up or slows down.
Yes. The YouTube video showed calculating the net force, first engine force, minus friction.
Right.
Then using that net force to find the network over distance. And then setting that network equal to the change in kinetic energy, throughout 1 FE4, FE2, to figure out the car's final speed.
That's a neat way to tie it all together. Net force, network, and your change in kinetic energy.
It really shows the links beautifully.
And underpinning all of this, as you said, is that big idea. Conservation of energy.
Always. Energy cannot be created or destroyed in a closed system. It just gets transferred or transformed. Siavula mentioning heat from brakes is a transformation.
And you mentioned the University of Johannesburg source tackled a common misunderstanding here about energy being used up.
Yes, that's a really common misconception. Students and, well, lots of people talk about energy being lost or used up.
Mm-hmm.
The UJ content stresses that it's really about transformation.
So when the brakes do negative work, the kinetic energy isn't destroyed.
It's converted mostly into thermal energy, which then dissipates into the surroundings. It's still there, just less useful perhaps for moving the car. The total energy is conserved.
Okay. Now, thinking about these forces, we've mentioned applied forces, friction, gravity implicitly. Are there different types of forces and how they handle energy? This sounds like it might lead to conservative and non-conservative forces.
That's a great connection to make. While our specific Siavula bits didn't explicitly define them, the concepts are definitely there. Conservative forces, like gravity, are special.
How so?
The work done by a conservative force when moving an object between 2 points doesn't depend on the path taken. Only the start and end points matter.
Okay.
And if you move an object in a closed loop, start and end at the same place under only conservative forces, the total work done by that force is 0. Think lifting a book up and putting it back down. Gravity does negative work going up, positive work coming down, and they cancel out.
So the energy associated with gravity, its potential energy, can be sort of stored and fully recovered.
That's a good way to put it. Now, non-conservative forces are different. Friction is the classic example.
And how do they differ?
The work done by non-conservative forces does depend on the path. The longer you slide something against friction, the more work friction does, and the more energy gets dissipated, usually as heat.
And that energy isn't easily recoverable, is it? It just spreads out.
Exactly. It's generally lost from the mechanical energy of the system, kinetic plus potential. The UJ source actually noted a confusion where students sometimes mix up non-conservative forces and momentum conservation.
Oh, how so?
Well, they clarified that non-conservative forces primarily impact mechanical energy, turning it into other forms like heat. Momentum conservation is about external forces acting on a system. Different concepts.
Got it. So non-conservative forces, like friction, essentially drain mechanical energy from the system by doing work, often negative work.
That's the main effect, yes. They cause a change, usually a decrease, in the total mechanical energy, transforming it into non-mechanical forms like thermal energy. That's why things slow down and stop eventually due to friction or air resistance.
Okay, that clarifies the types of forces and their energy impact. Now let's shift gears slightly to power. Another common word, but what's the physics definition?
Power, in physics, is all about the rate at which work is done. Or you could say the rate at which energy is transferred or transformed.
So it's not just how much work, but how fast.
Exactly. How quickly is that energy changing? A powerful engine does work quickly. A less powerful one does the same work more slowly.
Makes sense. Our sources mentioned average power. How's that calculated?
The basic formula for average power is just the total work done divided by the time it took. So average frac work.
It's simple enough. Work over time.
Yeah. And there's a useful special case mentioned in the Understanding Work Energy material. If you have a constant force acting on an object, and the object moves with a constant average velocity in the direction of that force,
Okay.
then the average power can also be calculated as power to F times VUA, force times velocity.
Ah, force times velocity. So more force or more speed means more power, assuming they're aligned.
Right. It shows that doing work faster requires either a larger force or moving the object faster in the direction of that force. It's a handy shortcut in those specific situations.
Okay, let's try and wrap this up then. Key takeaways. Work needs force and displacement in the same direction. Positive work adds energy to the object, usually kinetic. Negative work removes it.
Right, often turning it into heat via friction, for example.
Net work, the total work, equals the change in the object's kinetic energy. That's the work-energy theorem.
Crucial links.
And underlying it all, energy is conserved. It just changes form. We have conservative forces like gravity, where work depends only on endpoints, and non-conservative forces like friction, where the path matters and energy gets dissipated.
Excellent summary. And finally, power tells us how quickly that work is being done or how fast energy is being transferred.
Yeah.
Here, P equals contour and head bear equals, it's always FV.
Understanding all this really does build a solid foundation, doesn't it? It connects so many ideas and mechanics.
It absolutely does. It helps you see physics not just as separate equations, but as an interconnected description of how things interact and how energy flows.
So for you listening, here's something to think about. Try seeing the world through this work-energy lens for a bit. When you walk upstairs, what work are you doing? Against which force? Where does the energy come from and go?
Yeah, or think about a car accelerating or braking, or even something simple like stirring your coffee. Where is work being done? What energy transformations are happening?
Exactly. Look for these principles in action. It's kind of fascinating once you start noticing it everywhere. How does energy flow and change in the world around you? Give that some thought.